So let's continue our conference, and now we will have the invited speaker from Kaunas University of Technology, Professor Antanas Verikas. Let me introduce shortly his experience. Antanas Verikas worked at Halmstad University, Sweden for more than 25 years, was head of Department of Intelligent Systems, and his research interests include machine learning, deep learning, computer vision, pattern recognition, classification, information fusion, fuzzy logic, and visual media technology. His experience is shown by more than 200 scientific publications. And today's topic is data mining-based prediction of athletic performance. And so the floor is yours.
Thank you for introducing me, and I would like to start my talk by thanking organizers for inviting me to this conference. It's an honor to be here. And first of all, I would like to say why I'm talking about this and what is the relation to electronics of my talk. So nowadays, this increasing interest in human activity, and there are a lot of companies which develop software and hardware for monitoring human activity and also for predicting performance, for looking at trends. And this predictive performance is quite important for athletes. They want to know what levels they will achieve if they do different training programs and so on. So therefore, it seems relevant even for this conference electronics, what we are doing here. So this is the content of my talk, and you also will see on the top of the screen there is a content, and you can follow from there too. So on the left-hand side is the sections, and on the right-hand side will be subsections of my talk. So you can easily follow where I am in my talk. So it's quite additional content. I'm going to talk about the task, then how we collect data and methodology, then experimental investigations and conclusions at the end. So I will start with this, the task. What's the task we have here in this project? So we are having here two types of sports. So it's bicycling and golfing. So if you look into golfing, it seems that it's quite easy to make a shot, but in fact, the shot is quite complicated, and you will see that from the analysis what we did. So then, more specifically, so the task concerning cycling is we want to develop trainable algorithms that can assess physiological parameters of athletes using EMG data. So EMG is electromyography, stands for EMG. So I think quite many of you know what does it mean, electromyography. So it's signals coming from muscles. And using those signals here, we want to predict blood lactate concentration and also oxygen uptake. Blood lactate concentration is very important for athletes. If you reach some levels of blood lactate, then it's impossible for you to win competition. You have pain in your muscles and that's it. So therefore, they would like to monitor blood lactate levels and also to predict. So concerning golfing, we want to explore relations between muscle activity and the mechanics of golf swing. So as already mentioned, this swing is quite complicated one. So usually swing is split into three phases. I am returning back to the previous slide. So here you see the golfing when you have the first phase of the swing. It is called this backswing. So you rotate your body and you put, then by doing this, you put club behind your body. And then from that, you do this downswing, so-called. And then after that, it's a follow through. These three names are used to characterize golf swing. And this is quite complicated one. And we want to here to see the relation between the swing, the biomechanics of the swing, and also to relate this to the muscle activity, which muscles and combinations of muscles are involved to produce a good golf swing. So in addition, we want to predict here also this ball carry distance and club head speed. So these are two main parameters to characterize how successful was a golf shot. So these are the tasks in this research. So I start from data collection. First of all, bicycling. So you see a picture on the left-hand side, and here it is shown that some stationary equipment used here. So it's in this experiment we collected data concerning this oxygen uptake, so-called VO2. So you may see that the woman has in her mouth some tube, and you can measure that by this oxygen uptake. And also stationary equipment to record this EMG data. But of course, nowadays you can record using just portable, very simple portable equipment to record EMG data. And on the right-hand side, you see how this EMG signal look like. So here you see from 6 channels, but we used here in this research these muscles from 2 legs and 4 muscles from each leg. So here is rectus femoris, vastus lateralis, these 2 names, and then just from the front side and from back side, we use this biceps femoris and also semitendinosus. So why these muscles? There is research telling that these muscles are important or are used by athletes when you ride a bike. So here, what we do with these signals. So we want to extract simple features which allow to get some insights into biomechanics. So we don't want to just to get a good prediction, but also to try to understand why you get these good or bad results from those signals we record. So, but of course, we also want to get these predictions, physiological parameters using linear and nonlinear models. And the last subtask is to assess different features we extract, how important those different features are. So these are the tasks concerning cycling. And the features we extract, as I mentioned, we want to extract very simple features from those signals. So we call them timing events-based features. So I just show here 2 examples from these 2 channels. And these from 2 muscles, there is just the start of this activation phase. So this is activation of a right rectus femoris RF. And so it's NC, and then vastus lateralis, so right and left. We use this notation here. So we use those times activation and deactivation of those muscles. And then use this information to compute very simple features. Those features are like here. So it's phase shift from 2 different muscles, and these active time percentages of a muscle. And also we look into these means of those extracted features and standard deviations over a sliding window. So we choose some number of pedal revolutions, and we compute these statistics of those features. And also, of course, symmetry between for each feature between legs, right leg and the left leg. So these you may see that those features are very simple. They just timing events, and from those features, it turned out that we can draw some conclusions how different legs are used and what is important for athletes to get good results. And for prediction, we used the random forest. You see here a sketch of a random forest. So what is it, a random forest? Maybe most of you know, but I repeat that anyway. So it's a forest is a number of decision trees. So you see here in my sketch, tree 1, tree tree 2 and 3B. So number of trees. So what is specific here that each tree you design using some called bootstrap sample. So its bootstrap sample is created from a training set. This is of the same size. So you include randomly data from the training set, but you allow repetitions. So several data points may repeat twice or 3 times, but and it means that then some of them will be kept away. So this is which are kept away. They are not used to design tree. They are called out of bag, and those can be used to check how good specific tree is. So this is important that we create a tree using this randomness. You choose randomly data from a training set, and then when you try to get this to split, to make a split in a tree, so you select randomly a number of features, available features. This number n is smaller than this, n is smaller than the number of available features, usually it's square root of available and so on. So, and from those, you select the best. So it's again also some kind of randomness here that you select features randomly, and then from those you choose the best. So this randomness it's very important to get those trees not so correlated. So correlation, in fact, quite little you get in this random forest. And then you just to make a prediction or classification. So you just take voting or for regression you take average. So this is how it works random forest. So we use this random forest to make these predictions of athletic performance. So in this case for cycling, so it will be to predict those physiological parameters, this oxygen uptake and blood lactate concentration. So we extract simple features and then put those features into a random forest, and the random forest predicts those physiological parameters. And now I'm going into this methodology for golfing. So golfing is this short. I also mentioned I do not play golf by myself, but I know from the study that golf swing is quite complicated one. It's not so easy to do it in the right way. So on the right-hand side, you see this. On y-axis, you have this revolution of your body parts. So body parts here split into 4, what should I say, pieces. You have this club, you have leading arm, you have your chest and your hips. So this correct swing should go goes from the left to right, and this your body first is rotated back. And then, so you do this back swing. So your body rotates back, all those body parts. And then at some moment, you start rotating forward your body to the opposite direction. So this, and then it is shown when this happens. So if you look here, so it's called transition. So here you see at the first, this transition point is hips. So first of all, hips should change the direction of rotation. After that, should chest, then leading arm, and then clap. So this is a correct sequence. So this is from different studies have shown that this is a correct sequence, and then you can get a good shot if you get such sequence of rotation of your body parts. So. So we studied here. So this is, as I said, on the y-axis, you have this rotation speed. And our goal here was to relate this maximum rotation speed or peak rotation speed with this EMG signals, how different muscles are involved and into creating this good swing. So it's one task, and another task was how to predict this what from these EMG signals the parameters of the shot. So this ball carry distance, for example. So here it's again, you see how data were collected. So we have, I hope you can see that we have those here connection for EMG electrodes for on arm. You have here on shoulders and on the chest, on the back of the chest. So so we collect this EMG signal and signals, and in addition to that, also we use some biomechanical system, electromagnetic system to collect this biomechanical data, like these rotation speeds, and also this they measure also ball carry distance and angle and so on. So in addition to EMG data, there's biomechanical data we also collected. So here I show how these EMG data look like. So we used 8 channels, and as I showed on the picture, and one of those channels, in this case channel number 8, this one was used as reference. And here it was a task. First of all, we need to find out where is the start of these different swing phases. So it's after some filtering, so you can make a decision that, for example, here is a start from different channels. This starts the swing phase. So, and then these data were used to as a data vector. So, so 7 components here. So it's a starting time. So if you use this channel number 8 as a reference, so you can then compute which time it starts. For example, signal activity starts in channel number 7, and so on and so on. So, and this vector is used for further analysis, for prediction. And also we used this shape of these signals, how after some filtering, I will tell about that in a minute. But just here I show though how the data look like, the spread of the data. So on the left-hand side is for male. So we had in total we have, I think if I remember correctly, we had 10 males and 5 females. So this is how the data look like. So it's you see here ball carry distance on the y-axis, and you have club head speed on the x-axis. So you can see there is a correlation, not so very high, but anyways, this is statistically significant correlation between those 2 parameters. So if your club head speed is high, so also your distance also is longer. So your shot is you achieve a longer shot then. And this is for male, and this is for female. Female, we have fewer females, but it seems that they are more accurate in their shots. So the spread is not so big as for males. So these were the data collected and used to make those predictions and analysis and decisions. So I repeat, EMG data, and also I do not show here, but we also record this data concerning biomechanics. So here, what we do then with the data, which analysis we perform with the data. So we used here, first of all, canonical correlation analysis. I hope that most of you heard about this canonical correlation analysis. So what this analysis does is it finds a relation between sets of variables. So in our case, this one set of variables is this 8 EMG signals from these 8 different muscles. And then the other set of variables is these rotational speeds. So how body parts rotate. So we looked this into this thorax. Thorax, in fact, is chest. Pelvis is your hips and arm. So we wanted to look what is the correlation between these sets of variables, not just one variable, two variables as a pair, but also between sets of variables. And the canonical correlation analysis used well for that. So why we are doing this? So we want to see if you may expect that these peak rotational speeds, you have some good pattern of those peak rotational speeds. And this good pattern, I mean that these speeds lead to a good shot. And this pattern of rotational speeds is related to some pattern of these EMG signals. And then we want to study then how those patterns look like. Therefore, is this canonical correlation analysis here comes in. So it's one task. Another task is to predict those peak rotational speeds from EMG signals. So we looked is it possible to predict those peak rotational speeds from EMG signals and how good the prediction could be. So here we used these linear and also nonlinear models for that. And also the third task here was to this comprehensive characterization of this multi-channel EMG. As I showed you, these EMGs. So this is multi-channel EMGs, and we want to characterize them quite detailed characterization, and then use this to predict, to get those predictions as good as possible to assess this effectiveness of this golf shot. So these were the tasks and methodology to study data recorded from golfers. So I just 2 or 3 slides concerning this canonical analysis, what we do here. So as I already mentioned, that canonical correlation analysis try to find relations and to assess how many dimensions the variables are related for in one set related to the other set. So you may expect that you will get some relation, some direction, and in that direction you have this good correlation between sets of variables. So we wanted to see how well these variations in this peak rotational speed can be explained by this EMG data and also the vice versa, so I also mentioned. So canonical correlation analysis is just a linear technique. So here you see the covariance matrix of the data. So we have this X data. So in X data, let's say we have these EMG signals. We have 8 variables here, and we have Y signals. There's another set of variables, and here there are 3-dimensional data since we looked into this three speeds, rotational speeds. And this covariance matrix is used to get those new projections. So we say that we compute those canonical variates. So it's a pair. So you see here that we have this one variate U and another variate is B, and they are found by looking into this, finding canonical vectors, alpha transpose and this beta transpose. So we are looking for such directions where correlation is maximum between these transformed projected data. So this is expressed like this. So we are looking for these canonical vectors, and trying to maximize correlation between those projected data. And this is their constraint. So it's in fact a linear technique, very simple one. So at the end of analysis, you get this sequence of correlation coefficients, so which shall tell you how strong this relation is. And then you look at these canonical vectors. This gives you directions, and also this new canonical variates, new data. So what you get from this canonical correlation analysis. So how we characterize their EMG data, as already said, that we first of all we compute those initial points where this band swing peak starts, and then we also filter the signals, and after that we extract peaks, and from those, you see here on the bottom of the figure, you see all possible peaks extracted by the software. And on the top, you see two highest peaks, is number 10 and number 11. And those peaks, then we characterize those peaks by computing different parameters like position, height, width, and so on, area, and so on. So these quite simple parameters. So we used one peak and two peaks then to characterize EMG signals. So, and now I show you is quite a lot of different, we construct quite a lot of different feature sets to characterize those signals. So in fact, we have these 4 different sets of feature sets. So it's a channel statistics here. The first set of features. Here you see how many features we have in a feature set. Then we have these properties of the first peak, properties of the second peak, and properties of both peaks. So you don't need to look into details. I can email details if you want to. But in fact, in total, we have these 22 feature sets. So it's feature sets. So if you add everything together, so you will see these how many features we use. So, but then we put those features into a random forest. First of all, each feature set was used by a single random forest to get a prediction. And after that, those 22 predictions were put in another random forest. So this is a next level. And from that prediction, we got these final results. So this is again random forest, as you may see. And also we looked into this random forest is a very good tool for data mining, not just for prediction and classification, but also, for example, detect outliers and to assess importance of variables. So here I see we use this feature how to assess importance of variables. This is a very simple way to assess features. So what we have here, so B is the number of trees in the forest. Then this OOB, I mentioned that this is out of back data set, which is not used to design a tree. And this is true. So it's this. The first one is when you count the number of correct classifications you do with this tree. And then the next one is the number of correct classifications when you randomly permute this feature in the data set you have. So you may expect that if feature is important, then when you permute, the number of correct classifications will reduce. So this is the difference. If the difference is very small, it means that that feature is not very important. So this is quite simple way to assess variable importance. So now I'm going to experimental investigations and the results. What we got very quickly. So here from bicycling. So here we see on the y-axis on the top, we have the coefficient of determination from a model. So it tells you how much variance is explained by the model. So the highest value is 1. So, and this is the number of features we used in the model. So here we have 50 at the end, and then we try to reduce the number of variables. You see this reduction on the bottom part of the figure. So here we start with 50 and then go back. And for example, here if you have at this point, so we have 10 variables remaining, and all those variables are shown here, which remains at this point. So you may see that the coefficient of determination is quite high, here quite close to 1. And even when you reduce, at the beginning we had 51 features, and we go back to reduce to 10, also the prediction is quite good. So this is for oxygen, for blood lactate concentration level, and this is for oxygen uptake, the same experiment. And here we have the reduced model. We try to eliminate features which include somehow the magnitude of the signal. So if you don't use the magnitude of the signal, then just timing events, for example, and then statistics of timing events, then you do not need to do this proper normalization of those signals. And this normalization is quite it's not very clear how to do this good normalization. There are a lot of different suggestions how to do. So, and here you see what we got here. So it's also quite good results. So it's a little bit lower, the coefficient of determination, but anyway, it's also quite high. Next, you may see what we got. You can compare the full model when we used all the features, and also with this reduced set of features. So this is for lactate and oxygen uptake, this coefficient of determination for the full model. And here, this is 95% threshold for that. And this is what we obtained with this reduced set. So you will see that this reduced the coefficient determination is higher than 95% level of the full model. And this is which features I use. So it's quite a few. So if you look here, so we have these 8 features here in the lactate concentration to predict lactate concentration level, and just 7 for this oxygen uptake. So it's quite good results using this reduced model. And now I'm going into these results obtained from golf studies. And these some statistics concerning canonical correlation analysis. So as you see, we have here 3 swings, and this analysis we performed separately for those 3 swings. And so you may try to understand those directions. So in fact, you get those directions and which have high correlation coefficient. So then we looked specifically into downswing and looked into this first this direction, first canonical vector. So you may expect that you will get some understanding from the analysis of those sets of variables, which give you these high correlations after projection. So here, so this is the canonical vectors, how it look like. So if you look into this for the downswing, so you look for the EMG signal. Maybe it's not so interesting. All these muscles are involved to some extent, some of them more than some of them less, and also there's different sign. But what is interesting here, so it's this, if you look into those rotational speeds, so if you look this thorax and pelvis, they come in with quite high coefficient, but not arm. So this, then we discussed with these coaches of golf players, and they say that this is expected since this arm is less coordinated during swing. So you have quite good coordination of your thorax and pelvis, but not very good coordination of your arm. So they say that maybe you adjust your arm at the last moment of the impact. Therefore, is not a high coefficient of participation of this signal. And then also what's interesting to see, when we try to predict this rotational speed from this EMG signal, peak rotational speed from EMG signals. And here you see this prediction for, this is for thorax data, and this is from linear model. And I listed here which variables are important here. So in this prediction, we use 2 swings, this back swing and the downswing. And so in total, it could be 18 variables. And this is, I wrote which are important in this linear model. And here you see this, the coefficient of determination. And here is from a random forest of nonlinear model, and also coefficient of determination. And also this variable importance computed using this, the way I explained earlier. So what is interesting here, that those variables which are important in a linear model, they're also important, most of them, in nonlinear too. So it tells that this determination of variable importance is quite good. So this is for thorax, is similar was results for pelvis, a little bit lower this coefficient of determination, but the same thing, that which variables are important here. So most of them also are important in the nonlinear model. And I do not show this for the arm, since arm was less as I said, is the less involvement of arms, so we expected that also the prediction results will be poor, and that was the case. And one more thing, so this is just for curiosity, we looked into these activation profiles for different players. So here we have these results from 5 shots, and for each player, 5 shots, and this is the moment where this activation and different muscle starts related to that channel number 8. So what was interesting here, that is these activation profiles are very stable. From shot to shot, these activations of different muscles are activated in the same way, the same profile, especially for those which are more experienced players. And this is prediction. Here we have prediction results for this the performance of different golfers. So here we see the prediction results, the regression task that they try to predict the distance of the shot. So it's actual distance and predicted distance. And here is the classification or decision, we say detection results. When you try to predict from those parameters we use, how good will be the shot compared to the average of each player. So you take one player, so you have average of that player, and then you try to predict if the shot will be better than average or will be worse than the average. And here you see the results. So it's 24% errors for club head speed and also ball carry distance, 32%. So in fact, it's also quite good results. Then you can tell from these the parameters computed from this EMG signal how good will be the shot. It will be above your average or be below your average. So I'm going to conclusions just to have some time for discussion if there will be some discussion. So what we shown here with this study that with this very small set of timing events, we can get a prediction, quite good prediction of these 2 important parameters, blood lactate concentration, oxygen uptake. And these algorithms can be implemented in quite simple electronics. So then, and what's interesting that oxygen uptake prediction models are reliant on interaction between legs, while this lactate concentration, these models are reliant on features extracted interaction between muscles of one leg. So this was an important observation, interesting observation. Then we also got this quite strong linear relation exists of EMG, these magnitudes and these peak rotational speeds, but this for thorax and pelvis, but not for arm. This relation with arm data was less accurate. And during the downswing phase, we studied this downswing phase, the coordination of thorax and pelvis is much better compared to the arm. So this is also an important observation for coaches who work with these golf players. And muscle activation profiles are stable from shot to shot, especially for most effective players. So, thank you. That's all from my side.
Thank you. Very interesting topic. And I would like to ask you one question. How those features were selected, initial features? After your experiments, you selected most informative features, but initial selection of features, how was done? Almost all possible features were selected, or by intuition, or how it was done?
If you think about this bicycling, for example, so first of all, we looked into this frequency domain. We tried to look to extract features from frequency domain, so we got some results. And then from that, we looked into, took one more step to extract time events, these timing events features that such features allow more insights, deeper insights into what's happening in your body. So we looked into features which we thought could be useful. So everything we thought it could be useful. So we use those features. So it's, I mentioned these 51 features, so it's not so many, but anyway.
Mhm.
So I think we had perhaps a little bit more from more channels. But there is, we use them also some specific knowledge from these coaches. What could be interesting to look for these for players and for cyclists and for golf players. So this was also information used.
Okay. And the main goal is to make better training plans, or what? What is the application of this method?
So the main goal is twofold or threefold. You can say that one is there to look into how training progresses. So you can look into these trends. You having those parameters, just monitoring. So then also there are companies which are interested in producing some small devices for and sell them, of course, for active people and for athletes. So it's one goal to look, therefore we look specifically into these time-based features, since they're very simple to extract and easy to implement in hardware. So it's one more goal was, and also to look that such study could perhaps help to prevent injuries. So injuries, if you can monitor, for example, for cyclists, detect this blood lactate concentration, which is quite important. If you go above that level, then you'll get some injury in your muscle, and it could be quite important injury, serious injury in your muscle. And also the same for golfers. So if your shot is not biomechanically correct one, and also if your muscles are involved to a too high extent, so you also can get injuries, and so this is one more goal of that.
Mm-hmm. Thank you. More questions?
Like to ask, what could you say about reliability? Is it a reliable system, let's say, and the research, can we trust on it, or still development is needed?
So it's a good question. Concerning reliability, I think we need to have more data. So those data sets we use, we are not huge. In case of cyclists, I think we had, I think around 16 or 17 cyclists we used. And golfers, we have 15, 10 men and 5 women. So it's, we would need here to, of course, it depends which aspect you have in mind. When we try, for example, try to predict the personal average or personal shot. So you assess that shot against of your average. So I showed the graph at the end. So in that case, I think this study could be, I think it's quite a reliable one, since you measure, you just use data from one person, and you check against the average. So I think it's quite good. But if you think about those, for example, we looked into which patterns of EMG data relates to which patterns of these peak rotational speeds. I think here we need studies for more athletes involved in the studies. So I cannot tell much about the reliability. So for some aspects of the study, yes, I think it's quite reliable results, these detection results.
Okay, I see. Thanks.
Thank you. Do we have any more questions? Algimantas has.
Yes, I have. Could you please tell how universal is this methodology? Maybe this methodology could help Lithuanian basketball players.
Yes, I think I don't know about basketball players, but I think it's basketball. It's my guess. I'm not coach, but I think if you think about golf and cycling, so you have specific muscles involved very much. You know those muscles which works a lot in those sports. But about basketball, I don't know. Maybe there are more muscles involved. Then the study could be perhaps more complicated. But at least I think you could do some study. It could be useful if you also add results, for example, from some video camera or something like this. So you could then this analysis of such data, for example, EMG, relate to a video, and from video perhaps you can characterize, even using some of this artificial intelligence, what's happening in that scene. So perhaps if you're jumping when you jump very high, or you have some collision, I don't know. So, but I think perhaps during this, when you have this, not exercising, you do maybe exercising also. So it could help, but I think it's much more complicated in the case of basketball. Okay, it's my guess, since I'm not, you know, you need to know the physiology, what's happening in your body, which muscles are involved here. So, yeah.
Thank you.
Okay, thanks. I think that's all. We finished almost exactly at time. And now we'll have technical break. And after the break, we will continue on session 4A, electronics, 1:30. So thank you all participants. Thank you, invited speaker, and see you later.
Thank you.